Hello everyone, welcome to the video in which we will see Unit 2 and Unit 3. In this video, we will be seeing on two-dimensional transformations, so which is a part of Unit 2. In many applications, there will be we need to apply changes in the size, shape and orientation of an object. So this is actually called as transformations. So when we apply these changes for a 2D object, it is known as two-dimensional transformation. So what is a 2D object is? Any object that is defined by two coordinate axes is known as two-dimensional object. So anything which can be drawn on a paper, that is with length and breadth, okay, as the dimensions. So there are five basic transformations that which we can apply on a 2D object, namely translation, rotation and scaling. Translation is used for moving the object from one place to another. Rotation, as the name suggests, it is used to rotate the object. And scaling, it is used to enlarge or decrease the size of the object. The other two transformations are reflection and shearing. Reflection is basically used to produce a mirror image of the object. We will see reflection in detail in the upcoming videos, but reflection is producing mirror image of the objects. And then shearing is deforming the object. So simple shearing techniques is to deform the objects, like moving the object. If an object is fixed to the surface and if we give a force on the top side of the object will not move physically, but it might get disoriented. So that property is known as the shearing property. So let us see one by one all these basic transformations. So first one is translation. Translation is to move the 2D point by adding a translation distance tx and ty from its original coordinate position x and y. So now if you take a point, let that point be specified by its x and y coordinates. When we translate it, let the new coordinates be x dash and y dash. So now the new coordinates will be the old coordinates plus the translation distance tx, and the new coordinate of y will be the old coordinate of y plus the translation distance ty. So alternatively, translation can be also be specified by a following matrix equation: 1 0 tx 0 1 ty 0 0 1. So we can rewrite this formula: x dash y dash 1 equals to 1 0 tx 0 1 ty 0 0 1 into x into y into 1. If you multiply this matrix and see, you will get the above equation, that is x dash equals to x plus tx and y dash equals to y plus ty. So for example, if we want to translate a triangle with vertices 10, 20, 10, 10 and 20, 10 by tx equals to 5 and ty equals to 10, we compute the following matrix. So if we put 10, 20 and then if we want to see directly, it will become 15, 30. So if you see, the answer will be 15, 30. You work out this matrix and see. I will be using examples to explain it more clearly. And if you see 10, 10, after adding tx and ty, which tx is equals to 5 and ty equals to 10, it will become 15 and 20. And 20, 10, after translating, it will become 25, 20. So this is this is about translation of a matrix. Next, we will see what is rotation. Rotation, as I have told you, it is rotating an object about certain angle. So let us take this question mark as the angle. So it can be you can consider this as theta. So this rotation can be in clockwise direction as well as anti-clockwise direction. When it is in the anti-clockwise direction, we will take positive values. Please remember, when we take anti-clockwise direction, we will take positive values. When we take clockwise direction, we will take negative values respectively. So the new coordinates are x dash equals to x cos theta minus y sin theta, and y dash equals to x sin theta plus y cos theta. This rotation technique can be converted into a matrix form as cos theta sin theta 0 minus cos theta minus sin theta cos theta 0 0 0 1. So this entire formula can be rewritten as x dash y dash 1 cos theta minus sin theta 0 sin theta cos theta 0 0 0 1. So if you cross multiply, you will get this above equation. So let us see the same one more problem. The triangle are having the same coordinates, but we are rotating an angle of 30 degrees. So instead of theta, if you substitute 30 degrees, you will get the new x dash y dash 1 value. So you can compute this in your calculator. So this is all about rotation. Next we'll go to scaling. So scaling is to enlarge or decrease the shape or size of the object. So generally we do scaling with respect to origin. Okay, so what is scaling is the new coordinate equals to the old coordinate multiplied by some factor. So this Sx and Sy are the scaling factors. So Sx is the scaling factor of x and Sy is the scaling factor of y. So this scaling factor is multiplied with the original coordinate to get the new coordinate. So this scaling factor, this multiplication of the scaling factor can be written in transformation matrix. So that is Sx 0 0 0 Sy 0 0 0 1. So this is the formula, and the entire thing can be rewritten as x dash y dash 0 Sx 0 0 0 Sy 0 0 0 1 into x y and 1. So if you multiply this matrix and see, you can get x dash equal to Sx into x, y dash equals to Sy into y. So let us see with an example. Let us take the same triangle with the same coordinates, and Sx equals to 2 and Sy equals to 1.5. If we apply this on the first coordinate, the x value is 10 when multiplied by 2 becomes 20. The y value is 20 when multiplied by 1.5 becomes 30. You can do it in calculator and see. And similarly, apply the same technique for the other two vertices also and check whether you are getting the same answer. So the next one is concatenation of properties of composite matrix. So composite matrix multiplication is associative first. So what it means is A into B into C can be written as A into B into C or A into B into C. So this is a very important property for matrix multiplication. So next, let us see about composite transformation matrix. So in composite transformation matrix is actually very simple. So instead of doing a single translation, if we do one translation at a time, then do another translation, instead of doing separately, if you want to do both the translation at a single time, that is known as actually composite transformation matrix. So this is the transformation matrix of the first translation. This is the transformation matrix of the second translation. If you cross multiply, you will get the sum of two translations in the transformation matrix. This demonstrates that two successive translations are additive in nature. So the same applies for rotation. If you want to rotate the object twice, first with an angle of theta and second with an angle of alpha. So now let us take both as anti-clockwise rotation itself for easy understanding. So this is the transformation matrix of rotation for angle of theta, and this is the transformation matrix for a rotation of angle of alpha. So what is if we multiply these two matrices, we can see that the final the final transformation matrix is the sum of both the rotations. So theta plus alpha, cos of theta plus alpha minus sine of theta plus alpha 0, sine of theta plus alpha, cos of theta plus alpha 0, 0, 0, 1. So this demonstrates that two successive rotations are also additive. Similarly, with the scaling process also, if we see, if we scale the shape first time with a scaling factor of sx1 and sy1, and then a scaling factor of sx2 and sy2, and this is, as we know, is the transformation matrix of scaling 1 and scaling 2. If we multiply this, we'll get a resulting matrix in which the scaling factors are multiplied. So it becomes the final transformation matrix becomes sx1 into sx2. So this demonstrates the two successive scaling with respect to origin are multiplicative. So the next one is general pivot point rotation. So till now we have seen normal rotation with respect to origin. But what happens if the object is like this and you want to rotate the object with respect to this point, the red point, which is xr and yr. So what we do in this situation is we actually move this point to the origin like this. So translate the point to the origin, then do the given rotation about that origin, and then reverse translate back that object to its original point. So that is what is given here. This is the general procedure. Translate the object so that the pivot point position is moved to the origin. So this point is moved to the origin. So then it becomes like this. Then it is rotated. Then it becomes like this. Then again it is this point is sent back to its original position. So it becomes like this. This is general pivot point rotation. So the corresponding composite transformation matrix you see first is translation. So here you first is what we have to do is in the composite transformation, what actually we are doing first will come in the right hand side, from rightmost side. Then what we are doing in the second will come to next to that, and what we are doing in the last transformation will come in the most left hand side of the matrix. So this is applicable when we are using column matrices. So in terms of column matrices I'm saying is just a minute. So when we are doing like this is a column matrix, this is not a row matrix. So when we do a row matrix like this one, so when x dash y dash 1 is present, then what we do is, then this part will come here. So what first we are doing, that will come in the left hand side, and what last we are doing will come in the right hand side. Now let us take the usual norm, which is the column matrix. So first we are moving this point to the origin. So we are moving this by a position minus xr yr. So this is that one. Then rotating in angle theta, then moving it back with a position of xr yr. So if you multiply it, you will get the resulting answer. So this will be the resulting answer. So similarly, same for general fixed point scaling. You translate the object to the origin, enlarge or reduce the size of the object, then translate it back. The composition matrix is given in this form. So this is the composition matrix of that one. So there is one more thing about scaling. In general direction scaling along the arbitrary direction is not simple as scaling along xy direction. So when in xy direction it is very easy to scale, but in arbitrary direction what we have to do is we have to follow a set of procedures in which we can bring it back to the original position. So if this is the axis in which we are scaling, we'll rotate this object so that it coincides with the x and y x axis and y axis, then scale using the scaling factor s1 and s2, then rotate it in the opposite direction so that we'll get the original thing. So that will be the scaling matrix. See, first we are rotating it, then scaling, then opposite rotation. So this is all for this lecture, and in the next lecture we will be seeing about reflection and shearing matrices.